Hey guys, what's up? Eddie Alho here with KissAnalog.com. Alright, today we have a Class D audio amplifier. I have a whole bunch of them back here I was going to start reviewing, but I looked at a couple, started doing some testing, and I wanted to pull up this kind of high-endish Class D. I think this is actually a Class T, which is a form of a kind of an improved version of a Class D. So pretty nice. Toroidal inductors for the LC filter output, poly caps. It all looks like very nice construction. Poly caps on the input, WEMAs. You know, nice caps, nice rectifiers. Pretty nice heat sink across here. Seems like it's pretty nice construction. Okay, so like I say, I think this is pretty high-endish. Pretty high-end Class D amplifier, or you know, T. So I want to do an analysis on this thing, and I want to hook a power supply up to it. And we're designing a power supply, and I thought I can kind of meld my power supply into this one and get this guy running. I want to kind of use this as a kind of the golden standard until I find something to replace it, because some of these Class D amplifiers aren't really what they're cracked up to be, I don't think. So let's go down that road and see what we see. Like for instance, this one, I want to start off by looking at the gain across the frequency band, 20 Hertz, 20 kilohertz, and the phase. You'd want the phase to be 0. You don't want the output voltage and input voltage to be in phase with each other. Otherwise, you know, phase is like a timing thing. You don't want your wave shape to be out of time with your input. Now, if it was consistent, if you had say a 10-degree phase shift on the output all the way across the frequency band, that'd be okay. You never know that your input signal was 10 degrees ahead or behind. But what I've noticed on these things is that, and I think it's probably due to the LC filter design on the output, that at one point you get a phase shift, plus shift here, and a minus shift on this side. So we're going to take some pictures, and I'm going to show you two ways to do it. We're going to use the scope that anybody can do with any scope, and we're going to look at the input voltage and the output voltage, and we're going to look at the phase relationship between them. If they're in phase, they'll be right on top of each other. If they're not, they're out of phase. And so we'll look at that across some frequencies, and we'll be looking at the amplitude across those frequencies to see how steady it is. Okay? And then we'll use the FRA analysis on the Bode plot analysis kind of feature on this Instek scope to do it the quick and easy way. But we'll do it both ways, okay? And you can see how it's done. Alright guys, let's get this done. Alright, thanks guys. Alright, so this is the power supply, the GW Instek GPC3030D. It goes to actually 31.6 volts, not just 30. It has a maximum of 3 amps. The way I have this set up is I have it up in series mode with this button out, that button in, and I have the current all the way maxed out, voltage all the way maxed out. So I'll be able to go up to 3 amps max. Okay, so that way if I went like this, I can see the voltage on each one. So I can see it's plus minus 31.6 volts, but I'll monitor the current on one side and the voltage on the other. And so it connects these two guys internally, the plus minus, so that's my center point, and this is my plus voltage, my minus voltage. Okay, and for the setup, here's the power coming from the power supply. The green one is the center terminal coming to the terminal block here. Black is coming to this side. This is one of the AC inputs, and the red's in the other AC input, and it goes through the bridge rectifier. I'm powering both sides, but we're only putting a signal through the left side. So it goes through both bridge rectifiers to the capacitors and charges them up. So instead of going AC through, the diodes will they'll steer the plus minus voltage into the capacitors the correct way. And then here is the power module for the left side and the power module for the right side on this heat sink. And then here's the output LC filter. There's little C's down here in the L's and C's over on this side. And then we come out into this 8 ohm load resistor that's sitting on top of a 4 ohm just for heat sinking. Then we have the probes here, the differential probes here that come over to the Instek, set in the ×20 position. And this lead set here goes to the THD meter. And on the input, this comes from the function generator. And the scope probe is also connected down here. It's in the ×10 position. And then I have this fluke, it's 289, connected to one of the voltages on the output, the plus voltage. So it's right here, plus or minus red. So just monitoring that just for fun, even though I'm looking at it on the power supply up here. But I'll look at it here so I can see if there's voltage drop across these leads. And anyway, I'll show you the scope over here. Alright. One last thing is, this is the coax coming from the scope from generator 1 output. And I'll put this in here later to let the scope sweep through and do the FRA analysis. Okay. Before that, I'm going to just show you these LEDs. There's a red and a green LED for both. The red is ready and the green is power. And the other one is down here for this channel. And then when the relays kick on, after it does a power check, then you'll see that red LED come on. And I got the meter here so you can see the voltage as I increase it on the power supply. Okay, so here we go. I'm up to 31.6. And did you hear that relay and then the red light? Okay, I'll do it one more time. And maybe you heard the relay click off as I powered down. Okay, I'll bring in the voltage up kind of fast. You'll see these lights come on showing that we have enough voltage, everything's looking good. And then there's a time delay, and this circuit right here turns on this LED. So this circuit right here is kind of the power good circuit. Okay, so watch that. You can watch this voltage, and once I increase it, then I'll look over there for the LED. Alright, just one thing to point out is I changed this meter setup so that it shows me DC voltage down here, 31.685, and AC is 0. So there's no ripple. Those caps are charged up nice DC voltage right now. Once I apply a load, and then if I see some ripple voltage here, I'll call it out and tell you how much ripple I'm seeing here. For the scope setup, I've got the input voltage coming in here set at ×10 right there, and the differential probe on the output right here ×20, and you know, DC coupled. Both of them are DC coupled, so there we go. And then this scale here I'll be changing as I change frequencies, so we can, you know, so we can keep the waveform in view. Okay, here's the input. Let me turn on the power supply again, and okay, it's up to 31.6. You'll see the output click on. There it goes, clicks on. So this output is set for about, I would say, I have 82 millivolts going in. Well, here we go. 82 millivolts going in and 2.8 volts on the load. And roughly, let's just say that was 3 volts. That would be V squared over R. So it'd be 3 times 3 is 9 over 8 ohms. Would be a little over a watt. But since this is below 3 volts, it's probably close to a watt or a little bit less. Okay. Now, one thing right now, I can see I've got one of my probes on backwards. Let me straighten that up. Alright, so what we're going to do is I'm going to push these buttons in to center the waveforms, and we are at 10 hertz in right now. Okay, it's the scope's set at 50 milliseconds per division, and we're set up 4 volts per division on the output and 100 millivolts per division on the input. And you can see that there's a little bit of a phase shift between the blue and yellow waveform. Okay, I zoomed in so that you can see the scope better, but you can probably see the phase shift between the yellow and blue. I'm going to my scope measure button, hitting that, and now I've got the measure. I'm going to add a measurement, and I'm going to come over here to this screen here. See the phase? I want to add a phase measurement. Come down to phase, select that. Oops, this is a phase between channel 1 and channel 2, so I got to remove that one now. Okay, so I want to come down here in phase, but I got to change one of these to channel 1. So I'm going to check the phase between these. So here we go. See the phase? So I'm going to select that. Okay, so see we got about, it's kind of jumping around. So we're getting some noise, but it's around 30 degrees. It's kind of, you can see it bouncing around here. Okay, now I'm going to start increasing the frequency. And what we're doing is we're checking the amplitude to make sure that the amplitude here and here stay about the same. And at the same time, we're checking phase. We want to see, now it looks like they're in phase, you know, like this is going between 180 and 0 because they look like they're in phase to me. See that? Now this blue line is really noisy. See, I got the yellow one on top of it. So they might slightly be out of phase a little bit, if you notice that. But they're pretty close, right? Okay, 70 hertz. Let's go to 110 hertz. So there's, you know, maybe 10-15 degrees out of phase. They're pretty darn close. Okay, we're approaching 500. Let's see, that's 390. Okay, there's 500 hertz. And there's very little phase shift. And the amplitude has gone up a little bit on the, well, when I have to get enough cycles to get good math, but it's just under 3 volts here. Okay, we're at 1 kilohertz. Okay, that's 3 kilohertz. You can actually see for yourself where I am, because right there it gives you a readout. Okay, so we're at 3100 hertz. There's 5K. Now you can kind of see the phase shift. They're kind of moving away. The yellow was in front, now it's moving this way. It's not very much. It's really, this blue signal is really noisy. We'll talk about that in the next video, but in this video I just want to look at the gain and phase relationship across the frequency band. And I'm kind of showing you how to do it the manual way, kind of like just by a function generator and looking at the waveforms on the screen. But yeah, that blue one at the small signal level looks really noisy. Okay, we're at 15 kilohertz. You can really see it separating there. And that is 20 kilohertz right there. But you know, the amplitude stayed, I think the amplitude looked pretty flat. I mean, it's fairly flat throughout there. It's all just below 3 volts. So this is only 1 watt, so we're kind of at a small signal level. But there you go. For every frequency, we could take the output voltage divided by the input voltage. That'd be the gain. Take the log of that 20 times and plot it. Because if the input voltage is changing a little bit, then the gain of the amplifier is going to change this. But we want to see how flat the gain is across the frequency. So you really have to take into account the input changing as well. But you can see this is right around 30 degrees. And on the other end we're about minus 30 degrees. Okay, so I just dropped it down to 1 kilohertz. Watch, I'm going to lower the amplitude here on both the input and the output. Okay, because I'm going to increase the amplitude here. By the way, my fluke meter does not show any AC ripple at this point. Okay, right there, we're about 8 volts in. So that's about 8 watts, because 8 times 8 is 64 divided by 8 ohms. It's about 8 watts. Alright, okay, so now I'm going to drop this so we can increase a little bit higher. Okay, we're about we're right about 3 amps of my lab power supply. It's just kind of tripping the current limit. So that's kind of what happens. Now we're right at 3 amps, so that's my power supply on my bench clipping, not the audio amplifier. It's right there. It's about it's about 2.6 amps. Okay, we're about 2.9 amps, and so we have about 979 millivolts in, 35 volts out, RMS, and that's about 0.5 THD with noise. Okay, so I come up here and I hit the app button, and then it comes up the applications. This one's called FRA, Frequency Response Analysis, and then I hit select, and then I hit select again to confirm. Now I'm here and I'm ready to run my analysis, but I want to make sure I'm set up right, so let's zoom in. Alright, so then once I'm here, I go to setup, and I want to take output over input for gain. The output is on channel 2, so that's correct. Input is channel 1, so that's correct. Then the AWG Then the AWG generator, I hit that, and 20 hertz to 20 kilohertz. Yep, I want that. Yep, 20K. Okay, and then the amplitude, I'm going to set it at 0.9. I think that will make sure we don't clip my power supply on the bench. 50 ohm load, and I think we're ready to go. We're going to go 10 points per decade. I could go as high as 90, but I think 10 will give us enough resolution. Okay, now I just have to hit run. Okay, so we're ready to hit the run button, and it's setting up the frequency. It's starting here. It's 10 milliseconds per division. We're at 47 hertz right now. This tells the current frequency plot and the gain phase plot. Now the phase is right here, and it's kind of a straight line, so it's right around 0. It's about right. We don't. All right, guys. So here, let me set this up. This scale. I want to get a 0 over here. So let's go. We got to change this -6 down to 0, I think. Okay. Now we got a 0 on the graph, and the gain. It's at 5 dB per, and we got 31, so let's change that to 30. That'll give us a 0 over here. Because it auto scales, and sometimes it doesn't put the scale where you want it. Okay, and then also we'll do the measurement thing. We'll set up measurements. Cursor's on, and cursor 2 I'll put over here. Okay, let's just start with that, okay? Alright, so what that does, now what we wanted is straight lines on both of them, and what we got here, let me turn off the power supply for a minute because that load resistor is getting hot. So at the cursor 1 position, it's 30.94 dB with about 10.26 degrees, and cursor 2 is about 31.12 dB. So all the way across the band, I think that's about worst case. It was pretty darn close to 31 all the way across, and it's -22 here. So we're having a little bit of phase shift, and no phase shift there, and that's pretty much what we saw when we did it the manual way with the frequency generator and the scope, looking at the two waveforms. So this is just a quick way to plot it, and you can do it at different amplitudes. It makes it really quick and easy. Alright, okay, so doing a little bit of math on 31 dBs, divide that by 20, take the anti-log, it comes out to about 35, a gain of 35. So 1 volt RMS in gives you 35 volts RMS out. Alright guys, so what you may have noticed is there's some phase shift. It's not terrible, but there is some phase shift between input and output. I'm going to do a class AB amplifier, and we're going to see how that performs in comparison to this, okay? So we can see how an AB amplifier works in comparison to kind of an expensive, nice class D amp, okay? Alright, but for this video, hope you found that interesting. Thumbs up if you liked it. Thanks guys, appreciate it. See you next time.